Now we'll study recursive sequences and recursive relations. So we'll study recursive sequences and relations. Now basically in any recursive sequence, each term, it evolves from its previous terms. So basically any term, say an, will be function of terms before that. So an minus 1, an minus 2, an minus r. So basically it's a machine in which you feed the previous outputs as an input to generate the next term. In some sequences, this function f will depend entirely on one previous term. Say for example, your an plus 1, it is of the form fan, or it could be a function of two previous terms. So this an plus 1, it could be a function of an and an minus 1. We'll discuss different type of recurrence, and the first one is first order recurrence. Now in first order recurrence, this term will only depend on its previous term. So this an plus 1 will be some function of an. Say for example, an plus 1 equals 2an plus 1. So this is first order recurrence. When the term, it depends on this single previous term, this sequence, it is the orbit of the starting point. So basically what we are doing is we are starting from some point a naught, and then we are repeatedly applying this function. So a1 will be this f a naught, a2 will be f a1, which is f of f a naught, and this an will be f of f n times a naught. So one application will give a1, and the one will give a2, and this is how this entire sequence will be generated. Now this lecture is primarily concerned with the techniques that we can use to simplify and solve recurring sequences or relations. There are additional questions which are generally asked in the ISI and CMI, which relate to fixed point or limit points, monotonicity, boundedness. We have covered all that in a playlist called Real Sequences. I'll put the link to that playlist in the description below. So for fixed point, stability, global behavior, you can refer to that playlist. Then we can have second order recurrence. Where any term, it depends on previous two terms. So here an plus 1 will be function of an and an minus 1. Say for example, our famous Fibonacci sequence. So in this, we know that fn plus 1 will be equal to fn plus f n minus 1, where f1 is 1 and f2 is 1. And the type of recurrence is linear recurrence. So a recurrence is linear when the previous term appears only to the first power and not multiplied together. Say for example, an is some 3a n minus 1 plus 5, or an is 3a n minus 1 plus 2a n minus 2. So all these are linear recurrences. Now we'll study some common recurrence types, and the first one is additive recurrence. Now this is an plus 1 equals an plus d. Now, as you can see, clearly it is an AP. Second is multiplicative recurrence. So here you will be given an plus 1 equals r an, and clearly this is the GP. So an example for this will be an equals an minus 1 plus 3, and here we can write an equals 3 times an minus 1. Now this third type is linear first order recurrence. Now here an plus 1 will be expressed as some ran plus c. Now these linear first order recurrence, they are not GP, but they can be transformed into a GP. And to transform it to a GP, we'll need to find, step 1 will be find fixed point L. So what we'll do is, we'll replace these ANs with L. So we can simply write L equals RL plus C, or your L will be C upon 1 minus R. And then we'll subtract this L both sides. We'll form a pattern of a GP. Let us take up an example. Say for example, we are given this sequence which is an plus 1. It is 2an plus 3. Now first we'll find this fixed point. So it'll be L equals 2L plus 3. So value of L is minus 3. Now we'll subtract L both sides. So it'll be this an plus 1 plus 3. And this is 2an plus 6. So we can write an plus 1 plus 3. It is 2 times an plus 3. Now if we take an plus 1 plus 3 as some other sequence, capital an plus 1, and this an plus 3 as an. So this an plus 1 is equal to 2 times an, which is a geometric progression. So it will become a multiplicative recurrence. So in this, clearly this an plus 3, it is a GP. Then your fourth type is Fibonacci type recurrence. Here an is an minus 1 plus an minus 2, where a1 is 1 and a2 is 1, and the next term is sum of previous two terms. So this is memory based growth. So you must remember the previous two terms to generate a new term. So first two terms are 1 1, then 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, and this is how this sequence or recurrence is going to continue. Then we have this fifth type where we'll have recurrence with n. So it'll be of the form an plus 1 and it'll be equal to an plus n. Now in this sequence, differences are not constant, but they're natural numbers. So basically it'll become a series whose first difference are constant. So either we can solve them using this method where first difference are constant. We can generate first few terms of the series and then we can find am, or solve them using telescopic summation. Where the successive terms, they'll cancel out, and here it'll become sum of first and natural numbers or something. Now there are some techniques which are very useful in recursive sequences. So what I'll do is, I'll first discuss those techniques separately, and then in the end, we'll try to summarize everything with the illustrations. Now the first technique that we'll study in recurring relations is the linear theory and the characteristic equation. Now this theory, it works for linear homogeneous recurrences with constant coefficient. Say for example, C1A1 plus C2A2 Cnan equals 0. We can use this particular technique. Now to study this technique, we'll start with a second order linear homogeneous recurrence with constant coefficients. So suppose An is given as this C1 An minus 1 plus C2 An minus 2. Now we can see that this is homogeneous. All the powers are same and the coefficients are constants. In this, what we do is we'll write An as r to the power n, where r is unequal to 0, to generate the characteristic equation. And why do we do that? We'll come to it in some time. We can write this as r to the power n, and it'll be this C1 r to the power n minus 1 plus C2 r to the power n minus 2. Now we can cancel r to the power n minus 2. We'll get this as r square equals C1r plus C2, which is a quadratic equation in R, which we can write r square minus C1r minus C2 equals 0. Now roots of this characteristic equation, it'll supply the basis for our vector space. Now depending on the nature of roots, we can write the solution for this recurrence. So case could be the roots are distinct, where R1 is unequal to R2, or it could have equal roots where R1 is equal to R2 and it is equal to say R, or this third case when it has complex roots. So distinct roots, equal roots, or complex roots. Say the roots are of the form rho e to the power plus minus iota theta. Now, if the roots are distinct, then in that case, the solution to this homogeneous equation will be An equals some constant A, R1 to the power n plus B into R2 to the power n. We have actually discussed characteristic equations and the basis when we are studying matrices. For your reference, I'll provide the link to that matrices video in the description below. If the roots are real and distinct, then this An, it can be expressed as A R1 to the power n plus B R2 to the power n. Now, if the roots are real but equal, in that case, this An, it can be expressed as A plus Bn R to the power n. And if the roots are complex, in that case, this An will be given by this modulus rho. So rho to the power n into A cos n theta plus B sine n theta. And if we are given first few terms, then we can calculate these constants A and B. So for linear homogeneous equations with constant coefficients, this is the way to solve it. So if it is second order, you'll get a quadratic. If it is order 3, you'll get a cubic equation. So let us take up an example. Say for example, we are given a recurring relation which is defined as An equals 5an minus 1 minus 6an minus 2, and we are given that a0 is 2 and a1 is 5. For this solution, we let an as r to the power n. So it will be this r to the power n, 5 r to the power n minus 1 minus 6 r to the power n minus 2, which is r square minus 5r plus 6 equals to 0. Now we can write this as r minus 3 r minus 2 equals 0. So we get two real and distinct roots. So r could be 3 or r could be 2. Now when the roots are real and distinct, an is a r1 to the power n plus b r2 to the power n. So r a n, it could be expressed as this a 2 to the power n plus b into 3 to the power n. Now we are given initial values so that we can find the value of a and b. So when n is 0, a naught is 2. So this is 2 and will be this a plus b. And when n is 1, this is 5. So it'll be this 5 and this is 2a plus 3b. And clearly this is when a is 1 and b is 1. So nth term of the sequence, it is expressed as 2 to the power n plus 3 to the power n. So in this, we have used characteristic equation to solve this reoccurrence. Let us take another example when the roots are equal. Now in this case, we'll choose a recurring relation with equal roots. So let the recurrence be an equals 4an minus 1 minus 4a n minus 2. We are given that a naught is 1 and a1 is 4. Now again, we'll write an as r to the power n. So we'll directly write the characteristic equation. So it will be r square minus 4r plus 4 equals to 0, which is r minus 2 whole square equals 0. So here the value of r is 2. Now we know that in this case, this an will be a plus bn into 2 to the power n. Now when n is 0, it will be this a equals 1. So value of a is 1. And when the value of n is 1, we'll get a plus b into 2 equals 4. That is, value of b is 1. So for this reoccurrence, its nth term will be given by 1 plus n into 2 to the power n. Now let us also take another example with complex roots. Say for example, we are given this reoccurrence an equals an minus 1 minus an minus 2. Here a naught is 2 and a1 is 1. Now again, an is r to the power n. So we'll directly write r square minus r plus 1 equals 0, or r is 1 plus minus. Now this is root 3 iota upon 2. So this is 1 into e to the power plus minus iota pi by 3. So here rho is 1 and theta is pi by 3. So we can write this an as rho to the power n, which is going to be 1 to the power n 1, and this is a cos n pi by 3 plus b sine n pi by 3. Now when n is 0, cos 0 is 1 and sine 0 is 0. So we'll get a as 2. And if we put n as 1, so it'll be this 1 and this is 2 cos pi by 3 plus b sine pi by 3. Now cos pi by 3 is 1 by 2. So we'll get b as 0. So answer to this reoccurrence is its nth term will be given by 2 cos n pi by 3. Now this is a linear recurrence which is periodic, and the period of this function will be 2 pi upon pi by 3. So this sequence, it is periodic with period 6. So you're going to write first few terms. You can very easily verify this sequence. It repeats after 6 cycles. Now let us take an example where we have a third order linear recurrence with constant coefficients. Say for example, we're given that an plus 3, it is 6an plus 2 minus 11a n plus 1 plus 6an. Now this is linear, coefficients are constant. So again we'll let an as r to the power n. Now this is r cube equals 6r square minus 11r plus 6, or r cube minus 6r square plus 11r minus 6 equals 0. Now this is a very standard cubic equation, and we know that its roots are 1, 2 and 3. So it's an, it will be a 1 to the power n plus b 2 to the power n plus c 3 to the power n, and you'll be given 3 initial conditions to figure out the value of a, b and c. And to understand all this fully, you have to understand eigenvalues, eigenvectors and characteristic equations, which we have discussed in matrices. Now, why do we get this characteristic equation for homogeneous linear recurrence with constant coefficients? These recurrence, they are basically one linear map applied repeatedly. So if we have this second order equation, which is an equals c1 an minus 1 plus c2 an minus 2, we can write this in matrix form as an minus 1. It will be this c1 c2 an minus 1 an minus 2, and here we can write this as 1 and 0. We'll simply get an plus 1 equals an plus 1. Now we can write this again for this, then it'll be this c1 c2 1 0 square and then an minus 2 an minus 3, and if we keep doing this transform, we can write this as c1 c2 1 0 to the power n minus 1, and then it'll be this a1 a0. So what we are basically doing is we are applying this linear map c1 an minus 1 c2 an minus 2 repeatedly to get this recurrence an, which we can translate into this matrix equation, which is an minus 1. It is this matrix c1 c2 1 0 to the power n minus 1 a1 a0, and let this matrix c1 1 c2 0 be some m. So we can write this an minus 1 will be equal to m to the power n minus 1 a1 a0. So basically these recurrences, they are nothing but they are repeated matrix multiplication. Now for this matrix M, C1, C2, 1, 0. If you look at the characteristic equation, it will be this determinant of M minus lambda I, it is equal to 0, or simply determinant of C1 minus lambda C2 1 minus lambda equals 0, which is lambda square minus C1 lambda minus C2 equals 0, which is same as the characteristic equation we wrote, r square minus C1r minus C2 equals 0. So basically when you substitute this an as r to the power n, all you're doing is secretly finding eigenvalues for this matrix. And once you have this matrix equation, you know how to find these solutions in vector subspace. And that's the reason we are solving such recurrence relations using characteristic equations. So we have seen that we can use characteristic equations for linear homogeneous equations with constant coefficients. Now we can also use characteristic equations for non-homogeneous equations Say for example, we have an equation an equals, and say this is c1 an minus 1 plus c2 an minus 2, and goes on, and plus gn. So now we have this function of n, gn, and therefore it is non-homogeneous. Now in this case, what we do is we write the general solution as an equals an homogeneous plus an particular. So what we do is we find the solution to this equation considering a homogeneous part, and we find any one particular solution. So this is your homogeneous solution, and this is any one particular solution. So for a and h, we'll consider the homogeneous equation. So we'll consider this part, an c1 an minus 1, taking all the homogeneous terms, and we'll find their characteristic equation and roots to find this homogeneous solution. And for this particular solution, depending on this function gn, we'll try some standard solutions. So if gn is constant, then we can try this a and p as some constant, say capital C. If it is a polynomial of degree k, then we can take this a n as polynomial of degree k. If gn is some lambda to the power n, where lambda is not characteristic root, then we can try c lambda to the power n. And if it is lambda to the power n, where lambda is a characteristic root, then in that case, we can take this as cn lambda to the power n. So these are some of the standard particular solutions that we can try for an equation. Let us take up an example. Say, for example, we are given this equation, an equals an minus 1 plus an minus 2 plus 1. Basically, this is a Fibonacci sequence with this constant term plus 1. So first we'll write its homogeneous equation. It is an equals an minus 1 plus an minus 2. So it'll be this r square minus r minus 1 equals 0, or r is 1 plus minus root 5 by 2. Now we know that this 1 plus root 5 by 2, it's your golden ratio, and its conjugate is, say, psi 1 minus root 5 by 2. So this an will be of the form a 1 plus root 5 by 2 to the power n plus b into 1 minus under root 5 by 2 to the power n. Or we can write this as a and h will be a phi to the power n plus b psi to the power n. Now we need to find its particular solution, and this gn is of the form constant. So we'll let a and p as some constant c. Now we put it here, it'll be this c equals c plus 1. So c is just minus 1. So basically this a and p will be minus 1. So its general solution an will be this a and h, a phi to the power n plus b psi to the power n minus 1. So we have solved this non-homogeneous equation using homogeneous and particular solutions. Let us take another example. Suppose we have this equation which is an equals 5a n minus 1 minus 6a n minus 2 plus 2n. Now we'll directly write its homogeneous solution. So it'll be this r square minus 5r plus 6 equals 0. So that means value of R is either 2 or 3. So its homogeneous solution will be A to the power n plus B 3 to the power n. Now we'll find its particular solution. Here we have this linear term. So we'll write this ANPS sum AN plus B. Now we'll put it in this equation. So it'll be this AN plus B 5 AN minus 1 plus B minus 6 A n minus 2 plus B plus 2n. Now we'll find the value of A and B. So this is A n plus B. Now we'll compare the coefficients of n. So here it will be 5a minus 6a. So it will be this minus a plus 2n. And the constant term that we'll have here is minus 5a plus 12a. There'll be plus 7a minus b. Now we'll get a as 1. And if we compare the constant part, it'll be 2b equals 7a. So b will be simply 7 by 2. So its particular solution will be n plus 7 by 2. So general solution to this equation is a to the power n plus b 3 to the power n plus n plus 7 by 2. And if you are given initial values, you can find the value of these constants a and b. Let us take another example. Suppose we are given an equals 3an minus 1 minus 2a n minus 2 plus 2 to the power n, and we are given a naught equals 0 and a1 equals 1. Now first we'll solve its homogeneous part. So it'll be this r square minus 3r plus 2 equals 0. So r is either 1 or r is 2. So its solution will be a 1 to the power n plus b 2 to the power n, or we can simply write a plus b into 2 to the power n. Now for this particular solution, we have this of the form lambda to the power n, and here this lambda, it is characteristic root because we have one of the root as r equals 2. And once we have lambda as characteristic root, we try ANPS Cn lambda to the power n. So we'll try this particular solution as Cn to the power n. Now we'll put it in this equation. So it'll be this Cn to the power n 3 times Cn minus 1 to the power of n minus 1 minus 2C n minus 2 to the power of n minus 2 plus 2 to the power n. Now we can cancel out 2 to the power n minus 2. So it will be this 4Cn 6C n minus 1 minus 2C n minus 2 plus 4. Now this Cn term will cancel out. What we'll have here is minus 2C plus 4. That means value of C will be 2. So its particular solution will be 2n 2 to the power n, or simply n into 2 to the power of n plus 1. So its general solution will be a plus b 2 to the power n plus n into 2 to the power of n plus 1. Now we'll apply initial conditions. When n is 0, a0 is 0, so it will be this 0. This is a plus b, so a plus b is 0. And if we apply n as 1, we'll get 1 equals a plus 2b plus 4. So we'll get this b as minus 3 and a will be simply plus 3. So solution to this recurring equation will be an equals 3 minus 3 into 2 to the power n plus n into 2 to the power of n plus 1. Now there'll be questions in recurring sequences where they'll ask you to find the limit of recurring sequences. We have covered all that in real sequences. So here I'll just put the link of that playlist in the description below. So there we have discussed boundedness, monotonicity, anything and everything that you'll need to solve such questions, especially for ISI and CMI. We'll study this second tool separately, and it is rational recurrences or Mobius recurrences. So we'll study rational recurrences or Mobius recurrences. So these recurrences, they're of the form an plus 1 equals an plus b upon can plus d. So this family of recurrence relations is called a rational recurrence or Mobius recurrence. Now this is important not just for sequence and series recurring relation type problems, but also for functions, because clearly the same transformation, it's being applied again and again. So it is orbiting from A1. Then if we take this composition, then it will be A2. From A2 will go to A3. So basically this an, it is nothing but it is n minus 1 composition of this function to A1. Now when you have such type of problems, there are generally two conditions that occur. First one is periodicity. So in this, what we do is we compute f of fx, f3x, and if we have any case such that fkx is equal to x, then we say an plus k, it is equal to simply an, that is this sequence, it is periodic with period k. We are not going to use this much here, but we'll study this in functional equations. Here we'll just take up an example. Say for example, we're given an plus 1 equals 1 upon 1 minus an. Now basically if we compare it to function, then this function is fx equals 1 upon 1 minus x. If we consider f of fx, it will be 1 upon 1 minus fx or 1 upon 1 minus 1 upon 1 minus x, which will be 1 minus x upon minus x. And if we find f of fx, then it will be 1 upon 1 minus f of fx, which is 1 upon 1 minus 1 minus x upon minus x. So it will be simply x. So basically in this case, f3x is equal to x. So this function, it's periodic with period 3. So this sequence will be periodic with period 3. So if we take up an example, suppose for this sequence, a1 is 2. Then a2 will be 1 upon 1 minus a1. It will be simply minus 1. a3 will be 1 upon 1 minus a2, 1 by 2. a4 will be 1 upon 1 minus 1 by 2, 2. a5, 1 upon 1 minus 1 by 2, again minus 1. So in this sequence, the values are repeated after 3 terms. So what kind of problems you are going to get in rational recurrences is periodic sequences. Another example could be, we have this sequence an plus 1 equals an plus 1 upon an minus 1. Now this is equivalent to fx equals x plus 1 upon x minus 1. Now f of fx, It'll be fx plus 1 upon fx minus 1, which is x plus 1 upon x minus 1 plus 1, and x plus 1 upon x minus 1 minus 1, which is simply x. So this sequence, it is periodic with period 2. Now generally these functions have periods 2 or 3 or 4, and we'll discuss it in detail in functional equations. Now if the rational recurrence is not periodic, in that case we can use a very powerful transformation. So if we have this recurrent relation an plus 1 equals an plus b upon can plus d, and it has two distinct fixed points, say alpha beta, then what we'll do is we'll substitute yn equals an minus alpha upon an minus beta. And if we make this substitution, then this recurrence will change into a GP. First thing is how to find these fixed points. So for the fixed point, we know if it has a fixed point, all these terms, they'll converge to L. So it will be this L, AL plus B upon CL plus D. It will become a quadratic, and we are looking for a quadratic with two distinct roots, alpha and beta. Let us take up an example. Say, for example, an plus 1 equals 3an plus 2 upon 2an plus 3. Now, first we will find the fixed points. So this is L, and this is 3L plus 2 upon 2L plus 3. So it will be this 2L square equals 2, or L is plus or minus 1. So we have two fixed points. Now we'll substitute yn as an minus alpha. So it will be this an plus 1 upon an minus 1. We could take an minus 1 upon an plus 1 also. And now using this, we'll transform this equation. And since yn is an plus 1 upon an minus 1, what we'll do is we'll try and use componendo dividendo. So we can write an plus 1 upon an plus 1 minus 1 will be, now if we add them, we'll get 5an plus 5 upon an minus 1 will be this yn plus 1 equals 5 yn, which is nothing but a GP with common ratio 5. And for a GP, we can easily calculate its nth term, and once we have yn, we can calculate an using this form. Now in this, I have skipped a few steps. I did not check for existence of limit points, but if you are interested, you can always go to Real Sequences playlist to learn and understand it. Now you'll find certain problems where recurrence is going to lead to AGP. So we are dealing with recurrence sequence leading to AGP. So if we consider recurrence of the form an, and this is equal to some r an minus 1 plus alpha n plus beta. Now this r, it relates with common ratio of a GP, and this alpha n plus b linear term, it relates with an AP, and two successive terms, they are related like this. So we'll get GP behavior from R and AP behavior from alpha n plus beta. So what we'll do is we'll write this alpha n plus beta as some Fn. So we can write an as R an minus 1 plus Fn. Now we can write an minus 1 as R a n minus 2 plus Fn minus 1, and we can substitute this an minus 1 here. So it will be this an equals r into r a n minus 2 plus f n minus 1 plus fn. So this an will be r square a n minus 2 plus r f n minus 1 plus fn. Now we can expand a n minus 2. It will be r a n minus 3 plus f n minus 2. And if we put it here, we'll get this as a n equals r cube a n minus 3 plus r square f n minus 2 plus r f n minus 1 plus fn. And if we continue like this till a1, we can write this as an equals r to the power n minus 1 a1 plus r to the power n minus 2 f2 r to the power n minus 3 f3 up to fn, or simply an is r to the power n minus 1 a1 plus this summation where k varies from 2 to n r to the power n minus k fk. Now this fk, it is a linear part, so it's an AP, and r to the power n minus k, it is a GP. So in this recurrence relation, finding this n terms, it led to this AGP. So if we take a simple example, we are given this recurring relation an is 2an minus 1 plus n, and it says value of a1 is 1. Now we can write this an as 2 times, and an minus 1 is 2a n minus 2 plus n minus 1 plus n. So this an, it will be 2 square an minus 2 and plus 2n minus 1 plus n. If we write it for an minus 3, we can write this as an will be equal to 2 cube an minus 3 plus 2 square n minus 2 2n minus 1 plus n. And if we keep doing it for n times, we can simply write this as an equals 2 to the power n minus 1 a1 plus 2 to the power of n minus 2 into 2 to the power of n minus 3 into 3 up to 2n minus 1 and plus n. Now this part, it is an AGP. Now to solve this question, we have to solve this AGP, and here the value of a1 is 1. So we can write this as an equals 2 to the power of n minus 1 plus 2 to the power of n minus 2 into 2 to the power of n minus 3 into 3 up to 2n minus 1 plus n. Now we'll write the series again, but by shifting one term, so it will be 2 to the power n minus 1. This is 2 to the power of n minus 2 into 2. And here will be this 2n minus 1 and plus n. Now here the common ratio of GP is 1 by 2. So we'll multiply it with 1 by 2. So here will be this 2 to the power of n minus 2. Here will be 2 to the power of n minus 3. And this one, it will be simply n minus 1. Now if we subtract second from first, we can write 1 by 2 an will be 2 to the power of n minus 1. Now this is 2 to the power of n minus 2. This is 2 to the power of n minus 3. And in the end, we'll have this as 1. And then minus, we'll have 1 by 2 here. 1 by 2n. Now this is nothing but a GP. So this is 1 by 2 an will be 2 to the power of n minus 1 minus 1 by 2n. Now 2 will cancel. So we'll get this an as 2 to the power of n plus 1 minus 2 minus n. So this is the nth term of the sequence given by this recurring relation. So this is how we connect AGP to the recurring relation of the types an equals r an minus 1 plus alpha n plus beta, where this r will correspond to the GP and this linear part will correspond to the AP. Now generally we don't solve these questions using AGP because it takes a lot of time. A better way to solve it is using characteristic root plus trial solution method. This solution will always be of the form an equals an homogeneous part plus an particular part. So we'll call this as homogeneous part and this as particular part. Now first step is we'll find this homogeneous solution. So that's your step 1. We'll find homogeneous solution. In this homogeneous solution, if we drop this AP part, we'll get an equals r an minus 1, which is nothing but a GP. So we'll get this an as some constant into r to the power n, where this r is the characteristic root. Now we'll try and find a particular solution, and that'll be our step 2. So in step 2, we'll find this particular solution, and basically we'll assume r is unequal to 1. Since this case is linear, we'll assume that this particular solution, this a and p, will also be linear. So suppose it is some a n plus b. Now we'll substitute this solution in this equation. So we can write this as a n plus b will be equal to r into a n minus 1 plus b plus alpha n plus beta, which we can write as r a plus alpha n minus r a plus r b plus beta. Now we match coefficients of n and the constant term. We can write a equals ra plus alpha, and we get b equals minus ra plus rb plus beta. From here we'll get the value of a and b, and we'll get our particular solution. So we can simply write this a n as cr to the power n plus a n plus b. And if the value of r is 1, then we'll simply have this as a n minus 1 equals alpha n plus b, and we can solve this question using method of difference. So how do we apply this method? So let us take our previous example. So our question was an equals 2an minus 1 plus n. Now first we'll find homogeneous solution. Now for homogeneous solution, value of r is 2. So anh will be some constant c into 2 to the power n, and then we'll find its particular solution. And since this is linear, we'll assume A and P is A n plus B. So we can write A n plus B equals 2 times A n minus 1 plus B plus n by substituting this in this given equation. So it'll be this 2A plus 1n minus 2A plus 2B. Now if we compare these n parts, we'll get A as minus 1. If we compare the constant part, we'll get B as minus 2. So A and P will be minus n minus 2. So we can write this A n as C into 2 to the power n minus n minus 2. And we are given that A1 is 1. So if we put A1 as 1, so it'll be this 1, C, this is 2, this is minus 3. Value of C will be 2. So this AN will be 2 to the power of n plus 1 minus n minus 2. So this is another way of solving these recurrence relation. Now we can solve recurrences by iteration. And iteration simply means reapplying the recurrence again and again. So suppose we are given an plus 1. It is 2an plus 1 and a1 is 1. So a1 is 1, a2 is 3, a3 is 7, a4 is 15. And if we look at it, we can look at the pattern and it will be 2 to the power of n minus 1. And once we guess this pattern, we can solve it using principle of mathematical induction. Second method is solving by transformation. And we have already seen this in this example, an plus 1, and this is 2an plus 3. So here we have calculated a fixed point as minus 3, and then we can write this as an plus 1 plus 3. That will be 2 times an plus 3, which becomes a GP. So let us say this is some another sequence. Bn plus 1 is 2 times bn. So we can solve this sequence of bn, which is a GP, and then we can convert back bn to an. Third method is solving by summing differences. So here in this, we'll be given an plus 1 minus an. It'll be this fn. So we can use telescopic summation and write an minus a1. It'll be this summation fk, where k varies from 1 to n minus 1. And then there'll be some questions where you'll be given the ratio in terms of function. Say, for example, you'll be given an plus 1 upon an. This is some function of n. So in this, what we'll do is we'll multiply ratios. So we'll multiply an plus 1 upon an with an minus 1, an minus 1 upon an minus 2, and then a2 a1, and it'll be this fn minus 1 till f1. And here these successive terms, they'll cancel out. There we can write an plus 1 as a1, and then this product fk, where k varies from 1 to n. Now we'll summarize the transformation techniques which are worth mastering for recurrence relations or sequences. Now the first transformation technique is difference and ratio sequence. So if we have a sequence which is defined by this difference dn, which is an plus 1 minus an, then here we can use telescopic sum to find an, and it'll be equal to a naught plus this summation k varies from 0 to n minus 1 dk, or we may have a ratio sequencing such as Rn equals an plus 1 upon an. Now we can write this as an upon an minus 1 into an minus 1 upon an minus 2, and then a1 upon a naught, and it'll be this rn minus 1 up to r1. Now all these terms, they'll cancel. We'll get this ans, a naught, and this product k varies from 1 to n rk. Second technique is we can engineer a sequence for telescopic sum and products. Say, for example, we are given a sequence which is defined as an plus 1 equals an upon 1 plus nan, and we are given that a1 is 1. Now, if we take the reciprocal, we can write 1 upon an plus 1 equals 1 upon an plus n, which we can write 1 upon an plus 1 minus 1 upon an, it is equal to n. We can use telescopic summation now, since we have method of difference here. So we'll get 1 upon an as 1 upon a1 and plus this summation k varies from 1 to n minus 1 summation k. Now it'll be this 1 upon an. Now a1 is 1, so it'll be this 1 plus, and this is n minus 1 n by 2, or an will be simply 2 upon n square minus n plus 2. Now this third technique is invariant hunting. So basically in this, what we do is we try and transform our recurrence relation in such a way that we get some known sequence, an AP or a GP. So one of the example of invariant hunting is that rational transformation we did using fixed points. Fourth technique is basically reverse engineering. With this, what we do is we generally guess a right unknown looking at the different forms. If you're given a combination of terms, for the given combination of terms, we'll try and figure out what will simplify it, and then we'll verify it. So in this, we can use a lot of techniques, like we can take reciprocal, we can use logarithms, we can shift it by a quantity L. Say, for example, suppose we are given a sequence which is a1 equals 2 and an plus 1 is an square. So here basically a2 will be 2 square, a3 will be 2 square square, or 2 to the power of 2 square. If we generate the pattern, it will reveal this an, it will be simply 2 to the power of n minus 1. Now, we can do it with the reverse engineering. So, if we define a sequence Bn as log to the base 2 an, then it'll be this bn plus 1, it'll be 2 times bn. Now here b1 will be simply 1. So this bn, it is nothing but a gp with common ratio 2. So this bn will be 2 to the power of n minus 1. Now we can write bn is log an base 2, or this an is simply 2 to the power of n minus 1. So in this, what we have done is we have taken log. In another question, we may use shift transformation to find fixed point. So let us take up an example. Say, for example, we are given a1 is 1, an plus 1 is 3an plus 4 by 2. We have to find an. Now what we'll do is we'll find this fixed point L. So this is L equals 3L plus 4 upon 2, or value of L is minus 4. Now here again, I'll put a word of caution. Before doing this, we need to check if the limit point of the sequence exists. But here I'm just more concerned about how to use the technique. Now once we have this L, what we do is, in this recurrence equation, we'll subtract L both sides. So we'll get an plus 1 minus L and 3an plus 4 by 2 minus L, which in this case will be an plus 1 plus 4, and this is 3an plus 4 upon 2 plus 4. So this is an plus 1 plus 4, and this is 12. We can take 3 common, and it'll be 3an plus 4 by 2. Now if we take an plus 1 plus 4 as b, so let b and b an plus 4, we'll get the sequence as bn plus 1 equals 3 by 2 bn. Now a1 is 1, that means b1 is 5. Now this is nothing but a gp. So this bn, it will be 5 into 3 by 2 to the power n minus 1, and bn is nothing but an plus 4. So we can write this as an equals 5 into 3 by 2 to the power of n minus 1 minus 4. Then fifth one is characteristic equation. And we know that it is applicable for linear homogeneous equations with constant coefficients. And we have solved so many questions on it. Sixth one is non-homogeneous equations. This also we have solved. We'll just take a simple example. Suppose we are given a1 equals 1, an plus 1 equals 2an plus n. Now this is linear homogeneous, and this gn is linear. So first we will find homogeneous solution. So it will be this r equals 2. So in this, a and h will be simply a into 2 to the power n. Now for this particular solution, we'll try a and b as an plus b. So it will be this an plus 1 plus b 2 times an plus b plus n. Now comparing the coefficient of n, we'll get a equals 2a plus 1. So value of a is minus 1. And comparing the constant term, we'll get a plus b equals 2b, or a equals b. So b is also minus 1. So this a and p will be minus n minus 1, or this an will be a to the power n minus n minus 1. Now we are given a1 equals 1. Now we put n as 1. So a1 is 1. And this is 2a minus 2. So a is basically 3 by 2. So this an will be 3 into 2 to the power of n minus 1 minus n minus 1. Now, seventh is when a recurring relation can be transformed using an AGP. Then the eighth one is periodic recurrences. So these are some of the techniques that we can use for solving recurrence sequences and relations. Now here the questions. We are given this relation which is an equals an minus 1 plus 1 upon an minus 1 for all n greater than 1, and it is given that a1 it is equal to 1. Now it says we need to show that a75 will lie between 12 and 15. Now a1 is 1. If we write a2 is 1 plus 1. So a2 will be 2. a3 will be 2 plus 1 upon 2, which is greater than 2. And since it is an increasing sequence, any an will be greater than 2 for all n greater than 2. Now we look at this given condition. Now it says an equals an minus 1 plus 1 upon an minus 1. Now we square it, we can write an square as an minus 1 square plus 1 upon an minus 1 square plus 2. Now we know that this is always greater than an minus 1 square plus 2, because we are leaving out this positive term 1 upon an minus 1 square, and we know that any an it is greater than 2, then 1 upon an will be less than 1 by 2, or 1 upon an square will be less than 1 by 4. That means it will always be less than 1. So we can write it will be less than an minus 1 square plus 3. So from here we can write an minus 1 square plus 2 will be less than an square, and will be less than an minus 1 square plus 3. Now we can also write this as 2 is less than an square minus an minus 1 square, and will be less than 3. So we have this relationship that difference of squares of any two successive terms of the sequence will lie between 2 and 3. Now we'll start with n as 2. So we can write 2 is less than a2 square minus a1 square, and will be less than 3. And if we put n as 3, we'll write a3 square minus a2 square will be less than 3. And for n equals 4, we'll get a4 square minus a3 square will be less than 3. And we'll continue up to an square minus an minus square will be less than 3. Now if we add them all up, here this a2 square will cancel, a3 square will cancel. So all these terms will cancel. We can write 2 plus 2 plus 2 n minus 1 times. So there will be 2 n minus 1 will be less than an square minus a1 square, and will be less than 3 plus 3 plus 3 n minus 1 times, and there will be 3 n minus 1. Now we are given that value of a1 is 1. So we can write 2 n minus 1 plus 1 will be less than an square, and will be less than 3 n minus 1 plus 1. So this is the result that we have from the given condition. Now it says we need to prove that A75 will lie between 12 and 15. So what we'll do is we'll put the value of n as 75. So we'll put n equals 75. So this is 2 and this is 74 plus 1. will be less than a75 square will be less than 3 into 74 plus 1. Now this is 149. It is less than a75 square and will be less than 223. Now we know that 149 is greater than 144 and 223 is less than 225. We can write 12 square is less than a75 square and be less than 15 square, or a75 will lie between 12 and 15, and that is the answer to this question. Now the sixth question is, we are given the sequence of real numbers defined as u1, it is 1, and un plus 1, it is un plus 1 upon un for all n greater than or equal to 1. Now if we find u2 is going to be 1 plus 1, it will be this 2. u3 will be 2 plus 1 by 2, 2.5. So any ui, it will always be greater than or equal to 2 when I is greater than or equal to 2. Because we are adding something to un and it is clearly an increasing function. Now what you are going to do is, we are going to write this as un plus 1 square will be un square plus 1 upon un square plus 2, or un plus 1 square minus un square will be equal to 2 plus 1 upon un square. And this is the iterative relation we are going to use for our telescopic summation. Since we need un, we are not going to start with n plus 1, we have to start with un. So we can write un square minus un minus 1 square will be 2 plus 1 upon un minus 1 square. Next one will be un minus 1 square minus un minus 2 square, and there will be 2 plus 1 upon un minus 2 square, and will continue up to u2 square minus un square, and there will be 2 plus 1 upon u1 square. Now if we add all of them, then these successive terms they'll cancel, so we can write un square minus u1 square, and here this is 2 plus 2 plus 2, and it is from 1 to n minus 1, n minus 1 times, so there will be 2 n minus 1, and plus this is 1 upon u1 square plus 1 upon u2 square up to 1 upon un minus 1 square. Now u1 is 1, so this is 1, so we can write un square minus 1, and here will be this 2n minus 2 plus, now this u1 square again will be this 1, and this u2 square, u3 square and un minus 1 square, we know that any ui is greater than 2 when I is greater than or equal to 2. So 1 upon ui will be less than or equal to 1 upon 2, or 1 upon ui square will be less than or equal to 1 by 4 for any I greater than or equal to 2. So for all these terms from 2 to n minus 1, we can write this summation I varies from 2 to n minus 1, 1 upon ui square, it will be less than or equal to, now this is 2n minus 2 plus 1 and plus, now this is 1 by 4, 1 by 4, 1 by 4, n minus 2 times, so it will be this n minus 2 by 4. So we'll take this one on the right hand side. So this 1, 1 and 2 will cancel. So we can write un square will be less than or equal to, now this is 2n plus n minus 2 by 4, or we can write un square is less than, now this is 9n minus 2 by 4, Now this 9n minus 2 by 4 will be less than 9n by 4. If we take square root both sides, we can write this un, it will be less than 3 by 2 under root n, and which is what we need to prove in this question. Now here the question is, we are given a sequence of numbers a1, a2 up to a1005 which satisfy a1 upon a1 plus 1 equals a2 upon a2 plus 3 equals a3 upon a3 plus 5 equals a1005 upon a1005 plus 2009. And we are also given that a1 plus a2 plus a3 up to a1005 is 2010. We need to find the nature of this sequence. Now, since they are equal, let us write, suppose it is equal to 1 by k. So, for any AR, we can write AR upon AR plus 2R minus 1, it is equal to 1 by k, or AR k minus 1 equals 2R minus 1. So this AR will be 2R minus 1 upon k minus 1, where this k minus 1 is constant, and this 2R minus 1, it is nothing but an AP. So nature of this sequence is an arithmetic progression. Now if we look at this sum, which is A1 plus A2 plus A 1005, and this is 2010. So it is summation 2R minus 1, where R varies from 1 to 1005 upon k minus 1, and this is equal to 2010. Now sum of first odd natural numbers is equal to n square. So it will be equal to 1005 whole square, and this is equal to 2010 into k minus 1. Now if we cancel this, it will be simply 2, or k will be 1 plus 1005 by 2, or 1007 divided by 2. Now we need to find 21st term of the sequence. So we need to write A21, and A21 will be 41 upon k minus 1, and that will be 1005 into 2, which is 82 upon 1005. So answer to this question is, the sequence is an AP and whose 21st term is 82 upon 1005. Now here the question is, let A1 be unequal to 0, and for n greater than 1, we are given that AN equals n upon A n minus 1. Then we need to find the value of A1 into A2 up to A10. Now basically this is product of two consecutive terms. We can write AN into AN minus 1, AB equal to n. Now if we put n as 2, we can write A2 into A1 will be simply 2. If we put n as 4, we'll write A4 into A3 will be equal to 4. In the same way, A6 into A5, this is 6, and in the end we'll have A10 into A9, and will be equal to 10. We multiply all these terms, we'll get this product A1 into A2 into A3 up to A10, and there'll be 2 into 4 into 6 into 8 into 10, which is 2 to the power 5 into factorial 5, and that is 32 into 120, and which is 3840. So value of this product is 3840. Now here we are given a sequence of real numbers such that an plus 1 equals an plus under root of 1 plus an square, and a0 equals 0. If limit n tends to infinite, an upon 2 to the power n minus 1 is k by pi, we need to find the value of k. Now we put n as 0, we'll get a1, and this a1 will be a0 plus under root of 1 plus 0, which is 1. Now we can write this one as cot pi by 4, or basically we can write this as some cot theta, where theta is pi by 4. So this a2, it will be cot theta, and plus 1 plus cot square theta is cosec theta. So there will be cot theta plus cosec theta, and this is 1 plus cos theta by sin theta, and it is cot theta by 2. If we substitute here cot theta by 2, we'll get cot theta by 2 square. So a3 will be cot theta by 2 square. So we'll get an as cot theta upon 2 to the power of n minus 1, where theta is pi by 4. Now if we find this limit, which is limit n tends to infinite, an upon 2 to the power of n minus 1 will be this limit n tends to infinite cot theta upon 2 to the power of n minus 1 upon 2 to the power of n minus 1. We'll multiply it with theta and divide it with theta. So we can write this as limit n tends to infinite theta upon 2 to the power n minus 1 upon tan theta upon 2 to the power of n minus 1 into 1 by theta. Now when n tends to infinite, 1 upon 2 to the power n minus 1 tends to 0. So it is 0 upon 0 form. So now this is standard limit x upon tan x, which is 1. So value of this limit is simply 1 by theta, which is 4 upon pi. We are given that this limit is equal to k upon pi. So value of k in this is simply 4, and that is the answer to this question. Now here the question is, let a1 equals 0 and a1, a2, a3, an be real numbers such that mod of ai equals mod of I minus 1 plus 1 for all I, then arithmetic mean of these numbers has a value a, where which of the following is or are true. Now we square these, we can write ai square will be equal to ai minus 1 square plus 1 plus 2 ai minus 1, or we can write ai square minus ai minus 1 square, it is equal to 1 plus 2 ai minus 1. Now for this a, what we'll need is, we'll need a1 plus a2 up to an. So what we'll do is, we'll start from an plus 1 square minus an square, and it will be equal to 1 plus 2an. Then we can write an square minus an minus 1 square will be 1 plus 2 an minus 1, and we'll continue till a2 square minus a1 square, and it will be equal to 1 plus 2 a1. Now if we add these, all these successive terms, they'll cancel, and we know that a1 is 0, so this value will be 0. So from here we can write a square n plus 1, it will be 1 plus 1 plus 1 n times. So there will be simply n plus 2 times a1 plus a2 up to an, and we know that square of any number is simply greater than or equal to 0. Now if we divide everything with n, we can write 1 plus 2 into a1 plus a2 plus an by n, that is greater than or equal to 0. This is nothing but arithmetic mean of these values a. So we get 1 plus 2a is greater than or equal to 0, or a is simply greater than or equal to minus 1 by 2, and that's your option C. Now here we are given that consider a sequence of natural numbers S0, S1, S2 such that S0 is 3, S1 is 3, and Sn is 3 plus Sn minus 1 into Sn minus 2, then which of the following is or are correct? Now, if we look at this series, we know S0 is odd, S1 is odd. Now, if we look at S2, S2 will be 3 plus 3 into 3. Now, this is odd plus odd, so it will be even. So, we'll have S2 and this S2 will be even. Now, S3 is odd plus S1 into S2, so it will be odd into even, and odd into even is even, and odd plus even is odd. So, we'll have S3 odd. Now, S4 will be 3, which is odd, plus S2 into S3. So, this is even into odd, which again is even, and plus odd. So, this again is odd. So, S4 will be odd. Now, S5 will be odd plus odd into odd, and there will be even. So, this is even. So, we'll get even if and only if previous two terms they are odd. We'll have this series where S2 is even, S5 is even. So, basically S3n plus 2, it is even, and if it is a multiple of 3 or it is of the form 3n plus 1, then it will be an odd number. Now, it is asking for S1545 and S1546. Now, if we look at 1545, it is divisible by 3. So, this is 3 into 5, 1, 5. So, it's a multiple of 3. So, it is of the form 3n. So, this is odd. And 1546 will be 3 into 515 plus 1, which is of the form is 3n plus 1, which also is odd. So, both these numbers, they are odd. That means the correct option is this option D. Now, here the question is, let Fn denote number of different ways in which the positive integer n can be expressed as the sum of 1s and 2s. That is, say for example, f4 equals 5. We can write 4 as either 2 plus 2 or 2 plus 1 plus 1 or 1 plus 2 plus 1 or 1 plus 1 plus 2 or 1 plus 1 plus 1 plus 1. And we have taken these three as a separate entity. So here order is also important. So this Fn, it counts all the ways of writing a number in terms of the sum of 1s and 2s taken their order. Now if we look at F1, F1 is 1, and if we look at F2, we can write 2 as either 2 or 1 plus 1. So value of F2, it must be 2. Now we'll find Fn, which is number of ways of writing n in terms of 1s and 2s. Now there are two possibilities. In the end, we can have 1, or in the end, we can have 2. If we have 1 in the end, then all it remains is in how many ways we can write n minus 1 in terms of 1s and 2s. So this Fn will be equal to n minus 1, or that means we need to add this last number is 2, and if last number is 2, that means we have to express n minus 2 as sum of 1s and 2s. So it will be nothing but it will be f n minus 2. So basically this function, it follows Fibonacci sequence. So if we write f3, f3 is 1 plus 2, 3. f4 is 3 plus 2, 5. F5 is 5 and 3, 8. And F6 is 8 plus 5, 13. So value of F6 is 13, and that's your option B. Now the next one is find the value of f of F6. So we need to find f of F6, and f of F6 is nothing but it is F13. So we have to keep generating this series. Now F7 will be 21, F8 it is 34, F9 it is 55, F10 89, F11 4, 144, F12 144 plus 89, 233, and F13 will be 144 plus 233, and that will be 377. So value of f of F6 will be this option C. Now since we are adding previous two values, the value of Fn, it always increases. So it is an increasing function, and if it is an increasing function, that means this function is 1, 1. So this function is a 1, 1 function. But then if we look at the values, so we have pre-images for 1, 2 and 3, but we do not have pre-image for 4. So there are values which are missing from the range. So if this function is defined from n to n, then this function, it will be an into function. So this function is 1, 1 and into, and that's your option B. Now the question is, if alpha and beta are roots of this equation, then we can write alpha plus beta equals 1. Alpha into beta is minus 1. And if we solve them, and it says alpha is greater than beta, so its roots are 1 plus minus under root 5 by 2. So basically alpha is 1 plus root 5 by 2, and beta is 1 minus under root 5 by 2. And also, since alpha and beta, they are roots of this equation, we know they don't satisfy this equation. So alpha square minus alpha minus 1 must be 0. In the same way, beta square minus beta minus 1, it must be 0. Then the equation, we are given that an is alpha to the power n minus beta to the power n upon alpha minus beta for n greater than or equal to 1. And we are given that if b1 equals 1 and bn, it is given as a n minus 1 plus a n plus 1, then which of the following options is or are correct? Now first we need to simplify bn. So we can write this bn as a n minus 1. So there will be alpha to the power n minus 1 minus beta to the power n minus 1 upon alpha minus beta, and plus alpha to the power n plus 1 minus beta to the power n plus 1 upon alpha minus beta. Now we'll take alpha together. So we can write alpha to the power n minus 1, and then it will be 1 plus alpha square minus beta to the power n minus 1, 1 plus beta square whole divided by alpha minus beta. Now 1 plus alpha square will be 2 plus alpha. So we can write this as alpha to the power n minus 1, 2 plus alpha minus beta to the power n minus 1, 2 plus beta upon alpha minus beta. Now we know that alpha is 1 plus root 5 by 2 and beta is 1 minus under root 5 by 2. So if we put the value of alpha and beta here, we can write this is alpha to the power n minus 1, 5 plus under root 5 by 2 minus beta to the power n minus 1, 5 minus under root 5 by 2 whole divided by alpha minus beta. Now if we take root 5 common, we can write alpha to the power n minus 1, and this is 1 plus root 5 by 2 minus beta to the power n minus 1 root 5 minus 1 by 2 upon alpha minus beta. Now 1 plus root 5 by 2, this is alpha, and root 5 minus 1 by 2 is minus beta. And also if we look at alpha minus beta, so if we subtract them, this 1 by 2 will cancel, so we'll get this as root 5. So alpha minus beta, basically it is equal to root 5, and this is alpha to the power n minus 1 into alpha, so it is alpha to the power n and minus 1 is plus beta to the power n. So from here we can write your Bn, it will be alpha to the power n plus beta to the power n. That means this option B, it is correct. So this option B is correct. Now if we look at this option A, we need to find this summation n varies from 1 to infinite Bn upon 10 to the power n. Now Bn is alpha to the power n plus beta to the power n upon 10 to the power n. So basically it is alpha upon 10 to the power n plus summation beta upon 10 to the power n, where n varies from 1 to infinite. So both of them, they're infinite GPs. If we use sum of GP, it will be alpha by 10 and 1 minus alpha by 10 plus beta by 10 and 1 minus beta by 10. So there will be alpha upon 10 minus alpha plus beta upon 10 minus beta, which we can write as 10 alpha minus alpha beta plus 10 beta minus alpha beta upon 100 minus 10 alpha plus beta plus alpha beta. Now alpha plus beta is 1, so this is 10, and alpha into beta is minus 1. So 10 plus 2, 12 upon, and this is 100, 100 minus 10, 90, 90 minus 1 is 89. Value of summation Bn by 10 to the power n is 12 upon 89. That means this option A, it is incorrect. Now if we look at this option D is this summation n varies from 1 to infinite an upon 10 to the power n. Now an is simply summation n varies from 1 to infinite, and an by 10 will be alpha by 10 to the power n minus beta by 10 to the power n upon alpha minus beta. Now again, these are infinite GPs which will have same sum. So here we'll have minus sign, so we can write alpha upon 10 minus alpha minus beta upon 10 minus beta upon alpha minus beta. Now this is 10 alpha minus alpha beta minus 10 beta plus alpha beta. Alpha beta will cancel. So we'll get this is 10 alpha minus beta upon alpha minus beta, and this is 10 minus alpha and 10 minus beta. Now alpha minus beta will cancel. Now we have already solved this 10 minus alpha into 10 minus beta. So this value is nothing but 89. So this value will be 10 by 89. That means this option D is correct. Now the C is A1, A2, A3 up to AN. It is equal to AN plus 2 minus 1. Now for this, what we'll do is, we know that alpha square equals alpha plus 1, and we multiply it with alpha to the power n. We can write alpha to the power n plus 2. It is alpha to the power n plus 1 plus alpha to the power n. In the same way, we can write beta square equals beta plus 1. If we multiply it with beta to the power n, we can write beta to the power n plus 2 equals beta to the power n plus 1 plus beta n. If we subtract second from first, we can write alpha to the power n plus 2 minus beta to the power n plus 2 will be equal to alpha to the power n plus 1 minus beta to the power n plus 1 plus alpha to the power n minus beta to the power n. And if we divide everything with alpha minus beta, this is nothing but this is an plus 2, and this is an plus 1, and this is an. So basically, this sequence of terms a1, a2, a3, an plus 1, an plus 2, they are terms of Fibonacci sequence. Now here we need to find sum of n terms of Fibonacci sequence, which is a standard result, but we have to prove this result here. Now what we'll do is, we need an here. So we want to start with an plus 2 minus an plus 1. It is equal to an. Now an plus 1 minus an will be equal to an minus 1, and in the end we'll have a3 minus a2, and it will be equal to a1. Now if we add them all up, left hand side, this is telescopic sum, so all these terms will cancel. So we'll get an plus 2 minus a2 and will be equal to a1 plus a2 up to an. Now this is the sum that we need, and for this sum we just need to find the value of a2. Now a2 is alpha square minus beta square upon alpha minus beta. So it will be simply alpha plus beta, and alpha plus beta is simply 1. So if we put the value of a2 as 1, we can write this sum as a1 plus a2 plus an will be equal to an plus 2 minus 1, which is your option C. So the correct options are B, C, and D. Now in this question we are given an AP with first term 7 and common difference of 8, and T1, T2, T3 be such that T1 equals 3 and Tn plus 1 minus Tn is An, then which of the following is or true? Now we are given that Tn plus 1 minus Tn, it is equal to An. Now Tn minus 1, it will be An minus 1, and the same way T2 minus T1, it will be equal to A1. Now if we add them all, then all these terms they'll cancel. So from here we'll get Tn plus 1 minus T1, it will be equal to this series, which is A1 plus A2 up to An, which is nothing but sum of first n terms of this AP. Now this is Tn plus 1 minus T1. Now T1 is simply 3, and sum of n terms of this AP will be n by 2, 2a, and 2a is 2 into 7 plus n minus 1 into common difference of 8. Now this is 2 and this is 4. So this Tn plus 1 will be 3 plus n into 7 plus 4n minus 4. So basically this Tn plus 1, it will be 4n square plus 3n plus 3. Now first we'll find the value of T20 and T30. Now if we put n is 19, we'll get 4 into 19 square plus 3 into 19 plus 3. Now this value is 1504. That means this option A is incorrect. And for T30, we'll put n as 29. So it will be this 4 into 29 square plus 3 into 29 plus 3. And this value is 3454. That means this option C is correct. Now we have to find this summation. K varies from 1 to 20 and 1 to 30. So we have to simplify this summation. K varies from 1 to, suppose, capital N Tk, which is T1 plus T2 plus Tn. Now we can also write this as this summation. K varies from 0 to n minus 1 T K plus 1, because again will be T1 plus T2 up to Tn. Now this is summation. K varies from 0 to n minus 1, and this is 4k square plus 3k plus 3. So this is 4, and summation k square is n plus 1 to n plus 1 by 6. Here we are dealing with n minus 1, and 3, and n again is n minus 1, n divided by 2, n plus 3, and here this value, it will be n. Now first we'll find this summation. K varies from 1 to 20 Tk. Now here value of n is 20. So if we put n is 20, so it will be this 4 into 19 into 20 into 39 by 6 plus 3 into 19 into 20 divided by 2 plus 3 into 20. And this value is 10510. And summation K varies from 1 to 30 Tk. Now here we'll put n as 30, so it will be this 4 into 29 into 30 into 59 divided by 6, 3, 29 into 30 divided by 2 plus 3 into 30. And this value is 35615. So it is 10510. This is correct, and 35615. That means option D is incorrect. So the correct options are B and C. Now here the question is, let A and be a sequence such that A0 is equal to A1 and it is equal to 0. And we are given this recurring relation, which is AN plus 2. It is equal to 3 times AN plus 1 minus 2AN plus 1. Then we need to find A25 into A23 minus 2 times A25 into A22 minus 2 times A23 into A24 plus 4 times A22 into A24. Now here what we'll do is we'll take A25 common and A24 common. So here will be A25 and we'll get A23 minus 2 times A22, and here we'll take minus 2 A24 and we'll get A23 minus 2 A22. So basically we'll need to find this value, which is A25 minus 2 A24 into A23 minus 2 A22. So if we can find AN minus 2 AN minus 1, we'll get our result. So now we'll come to this given relation. So we are given that an plus 2 is 3 times an plus 1 minus 2an plus 1. Now we can take one of the an plus 1 on the left hand side. We can write an plus 2 minus an plus 1 will be equal to 2 times an plus 1 minus an plus 1. Now if we replace n with n minus 1, we can write an plus 1 minus an will be equal to 2 times an minus 1 plus 1, and we'll continue. And in the end, we'll have a2 minus a1 will be equal to 2 times a1 minus a0 plus 1. Now, if we add them all, these successive terms, they'll cancel. Here also, these terms, they'll cancel. And we also know value of a1 is 0 and a0 is 0. So from here, we can write an plus 2, it is equal to 2 times an plus 1 plus, now this is 1 plus 1 plus 1. Now from 1, it has gone to n plus 1. So there will be total n plus 1 terms. So from here we can say an plus 2 minus 2 an plus 1, it is equal to n plus 1. Or if we take n as n minus 2, we can write this as an minus 2 an minus 1 will be n minus 1. Now here we have a25 minus a24. Here the value of n is 25. So 25 minus 1 is 24. And a23 minus 2 a22, n is 23. So it will be this 22. So value of this result is 24 into 22, which is 528. So value of this expression, it will be 528, and that is the answer to this question. Now here we are given the sequence a1, a2, a3 such that a1 is equal to 1, a2 is equal to 2, and an plus 2, it is equal to 2 upon an plus 1 plus an, and we need to find value of a1 plus 1 upon a2 upon a3, a2 plus 1 upon a3 upon a4 up to a30 plus 1 upon a31 upon a32, and if this is equal to 2 to the power alpha 61c31, then we need to find the value of alpha. So first we'll look at what we need to prove. We need to prove a1 a2 plus 1 upon a2 a3 into a2 a3 plus 1 upon a3 a4 and a30 into a31 plus 1 upon a31 into a32. This is equal to sum 2 to the power alpha 61c31. Now since we have a1, a2, a2, a3, so we need product of an and an minus 1. So what we'll do is we'll cross multiply and we'll rearrange this as an plus 2 into an plus 1 minus an plus 1 into an, and it will be equal to 2. Now here we'll replace n with n minus 1. So we can write an plus 1 into an minus an into an minus 1 will be equal to 2. And we'll continue. And in the end we'll have a3 a2 minus a2 a1, and it'll be equal to 2. Now if we add them all up, all these successive terms, they'll cancel. So we'll get an plus 2 into an plus 1 minus a1 into a2 is 2, and this is 2 plus 2 plus 2. Now it goes from 1 to n, so there'll be 2n. So simply an plus 2 into an plus 1 will be 2 times n plus 1, or if we write an into an minus 1, so we'll replace n with n minus 2, so it will be this 2 times n minus 1, and this is the result which we are going to use to find the value of alpha. Now if we look at this left hand side, we can write this left hand side as this product ak into ak plus 1 upon ak plus 1 into ak plus 2, where the value of k, it varies from 1 to 30. Now ak into ak plus 1. So if you put n as k plus 1, we'll get ak plus 1 into ak, and will be equal to 2k, and ak plus 1 into ak plus 2 will be 2k plus 1. So we can write this as this product k varies from 1 to 30, and it will be this 2k plus 1 upon 2 into k plus 1. Now if we expand this product, if we put k as 1, we'll get this as 3, 5, 7. I'll go all the way up to 61. And in the denominator, we'll have this 2 30 times. So that'll be 2 to the power 30. And then we'll have k plus 1. So it'll be this 2 into 3 up to 31. Now, since we need 61C31, so what we'll do is we'll multiply numerator and denominator with the missing numbers. So we'll multiply 2, 4, 6 up to 60. And in the denominator will be 2 to the power 30. This is 2, 3, 31. And here will be 2, 4, 6, 60. Now, in the numerator, we'll have 2, 3, 4, 5 up to 61. So, numerator will be factorial 61. Now, this is 2 to the power 30. This is 2, 3, 4 into 31. And here, if we take 2 out from each of these 30 terms, so we'll get 2 to the power 30. And then we'll have 1, 2, 3 up to 30. So it'll be this factorial 61 divided by 2 to the power 60. And this is factorial 31 by factorial 30. So it'll be this 2 to the power minus 60, 61C 31. So this result, it is equal to 2 to the power minus 60, 61C 31. So that means value of alpha is minus 60. So for this question, value of alpha is minus 60. Now here the question is, we have this sequence where A0 is equal to A1 and it is 0. And we are given that AN plus 2 is equal to 2 times AN plus 1 minus AN plus 1. Then we need to find this summation. N varies from 2 to infinite, AN upon 7 to the power n. Now what we'll do is, we can write this recurring relation as AN plus 2 minus AN plus 1, and it will be equal to AN plus 1 minus AN plus 1. Now, if we put n as n minus 1, we can write AN plus 1 minus AN. It will be equal to AN minus AN minus 1 plus 1. I will continue up to A2 minus A1. And this is equal to A1 minus A0 plus 1. Now, if we add them all up, these terms, they'll cancel. Now, A1 is 0 and A0 is also 0. So we can write AN plus 2, it is equal to AN plus 1 and plus, now this is 1 plus 1 plus 1. Now this starts from 1 to n plus 1. So it will be this n plus 1. So from here we can write AN plus 2 minus AN plus 1 will be equal to n plus 1. So we have another recurring relation. Now from this recurring relation we can write AN plus 2 minus AN plus 1. This is n plus 1. AN plus 1 minus AN will be this n. And it'll go up to A1 minus A0. It'll be this 0. If we again add them all up, so we'll get this result as AN plus 2, A1 is 0. And this is 1 plus 2 plus 3 up to n plus 1. So this is sum of first n plus 1 numbers. So it'll be this n plus 1, n plus 2 by 2. Or simply we can write AN it will be n into n minus 1 by 2. So we have our an as n into n minus 1 by 2. Now we need to find sum of this series, which is this summation. N varies from 2 to infinite an by 7 to the power n, which is this summation. N varies from 2 to infinite, and this is n minus 1 by 2 into 1 by 7 to the power n. Now we know that 1 plus x square up to infinite, this is 1 upon 1 minus x when x is less than 1. So basically this is this summation x to the power n, where n varies from 0 to infinite, and this is 1 upon 1 minus x. Now we differentiate this, we can write this summation nx n minus 1, and it'll be equal to minus 1 upon 1 minus x square into minus 1. So there'll be 1 upon 1 minus x square, where n varies from 1 to infinite. And if we differentiate this again, we can write this summation n minus 1 x to the power n minus 2 will be equal to this minus 2 minus 1. So there'll be 2 upon 1 minus x cube. Now we need n minus 1 by 2 into x to the power n. So we'll multiply x square. So we can write n minus 1, we'll divide by 2, and we'll multiply x square. So there'll be x to the power n. So it'll be this x square upon 1 minus x cube, where n varies from 2 to infinite, which is the series that we need. Now here the value of x is 1 by 7. So it'll be this 1 by 7 square upon 1 minus 1 by 7 cube. So there'll be 1 upon 7 square, and this is 6 cube by 7 cube. So there'll be 7 upon 216. So answer to this question is 7 upon 216. Now here the question is, we need to evaluate this double summation. M varies from 1 to infinite. This summation n varies from 1 to infinite, and let this be s, and this is m square n by 3 to the power m, n into 3 to the power m plus m into 3 to the power n. Now what we'll do is we'll divide everything with m square n. We can write this as this sum as summation m varies from 1 to infinite, n varies from 1 to infinite, and this is 1, and we'll split as m and mn. So there'll be 3 to the power m by m, and this is 3 to the power m by m plus 3 to the power n by n. Now let 3 to the power m by m be am, and 3 to the power n by n be an. So we can write this sum as this summation m varies from 1 to infinite, n varies from 1 to infinite, 1 upon am, and this is am plus an. Now basically we'll write this as smn. If we write snm, it will be this summation n varies from 1 to infinite, and summation m varies from 1 to infinite, and this is 1 upon an, and this is an plus am. Now we know that in summation, variables are just dummies. So basically this is s and this is also s. So if we add them, we can write 2s will be equal to this summation m varies from 1 to infinite, summation n varies from 1 to infinite. Now we'll take 1 upon am plus an common, and we'll get this as 1 upon am plus 1 upon an. Now this is this summation 1 upon am plus an, and will be this am plus an upon am an. Now this am plus an will cancel. So we can write this sum as 1 by 2. This summation n varies from 1 to infinite. Summation n varies from 1 to infinite, 1 upon am into an. So basically this is this sum s, and this is 1 by 2. And since m and n, they are now independent, so we can write this summation n varies from 1 to infinite, 1 upon am into this summation n varies from 1 to infinite, 1 upon am. So basically we need to find this summation m varies from 1 to infinite, 1 by am, and 1 by am will be m upon 3 to the power m, and this is this summation n varies from 1 to infinite, n upon 3 to the power n. Now we'll use this result, which is, we know that summation x to the power r, where r varies from 0 to infinite, it is 1 upon 1 minus x when mod r is less than 1. And if we differentiate this, we can write summation r varies from 1 to infinite r x to the power r minus 1 will be 1 upon 1 minus x square, or if we multiply with x, we can write r varies from 1 to infinite r into x to the power r will be x into 1 minus x square. Now for this one, x is 1 by 3, and here also x is 1 by 3. So this s will be this 1 by 2, and this is 1 by 3 upon 1 minus 1 by 3 square, and this also is 1 by 3 upon 1 minus 1 by 3 square. So this sum will be 1 by 2, 1 by 9, and this is 4 by 9 into 4 by 9. Now this 9 will cancel, so it will be this 9 upon 32. So sum of this series is 9 upon 32, and that is the answer to this question.